Welcome back. So in this video lecture, we're going to do an introduction to the geometry of linear transformations in R2. So, and then there will be subsequent videos with more details. In this video, we're going to introduce what the basic linear transformations are, and then we'll talk about one type of linear transformation. And then in subsequent videos, we'll go through the other types. So the basic types of linear transformations in R2 are reflections in lines. And so the most basic reflections are reflections in the x-axis, or reflections in the y-axis, or reflections in the line y equals x. So these are basic, and other types of reflections in other lines can be represented by combinations of some of these basic types. Another type of linear transformation in R2 is called an expansion or a contraction. And now these expansions and contractions are also broken down into either horizontal expansions and contractions or vertical expansions and contractions. And we'll talk about those in another video. And then the last type, which is the trickiest type to understand and visualize, is a shear. And there are two types of shears, horizontal shears and vertical shears. So that's a later video. So there will be several videos on this portion of 6.5. And so this is really just the first 3 pages of that section of our textbook, and we're not going to do the rest of the section. This is plenty. So the people who care about these kinds of linear transformations are people who do computer imaging. So they need to know how to represent, because they use linear algebra in everything they do, but they need to know how to represent a transformation, a two-dimensional image, a transformation to another two-dimensional image. They need to know how to represent that with a matrix. And so these are all going to be 2x2 matrices. And these basic types that I just outlined here are represented by elementary matrices, elementary 2x2 matrices. And now you have to remember what an elementary matrix is. And I'll just remind you, an elementary matrix is a matrix that you get from the identity matrix with a single elementary row operation. And remember, an elementary row operation is a row swap, adding a multiple of one row to another row, or multiplying a single row by a scalar. So one of those operations on the identity matrix gives you what we call an elementary matrix. So these 3 building blocks are all represented by elementary matrices. So we're going to talk about reflections in this video. So the 3 basic reflections are across the horizontal axis, the vertical axis, or the line y equals x. Well, we've looked at the third type before, and I'm just going to remind you what that looks like. Reflecting across the line y equals x, taking a vector with components v1, v2. Reflecting it across that line means reflecting the terminal point, v1, v2, across that mirror. The line y equals x is like a mirror. And we get the vector, the image of v1, v2 is v2, v1. All we've done is swapped the 2 components. And remember how we got the standard matrix for that linear transformation. What we did was we took the 2 basis vectors for R2 and found their images. And so the image of 1, 0 is 0, 1. The image of 0, 1 is 1, 0. And then we lined those up as the columns. And that's the standard matrix for that linear transformation. And you can tell by looking at it, that's an elementary matrix. It's a single row swap on the identity matrix. Okay, so let's look at the other 2 types of reflections. we have a reflection across the horizontal axis, or the x-axis. So that means we're taking a vector v with components v1, v2, and reflecting it across the horizontal axis, getting a new vector, t of v, the image, and all we've changed is the second component. The first component remains v1, and then the second component becomes the opposite of v2, or negative v2. So once again, to get the standard matrix for that linear transformation, we're going to find the images of the two standard basis vectors. So 1, 0, which lies on the horizontal axis, E1 is 1, 0. If we reflect that across the x-axis, what happens to it? So reflecting a vector that lies on a line, reflecting it across that particular line doesn't do anything. So the image of E1 is just E1. So the image of 1, 0 is 1, 0. It doesn't move. And the other standard basis vector is E2. The components are 0, 1. If we reflect that, so that's sitting on the y-axis. If we reflect that across the x-axis, we get the new vector, t of E2, which does change. It is different. It's 0, negative 1. So we've just multiplied the second component by a negative 1. So then the standard basis, the standard matrix for that linear transformation is the matrix we get by lining up those two images, 1, 0, 0, negative 1, as the columns. And once again, we can tell by looking at it, it's an elementary matrix. That is just the 2 by 2 identity matrix with the second row multiplied by negative 1. Okay, so the last one is a reflection across the y-axis, or vertical axis. So let's see what that looks like. We take a vector with components v1, v2, reflect it across that vertical axis, and what have we done? Well, the second component hasn't changed. The first component, we're just multiplying the first component by negative 1. So the image of v1, v2 is just going to be negative v1, v2. So let's get its matrix, standard matrix. So we're going to look at the images of 1, 0 and 0, 1. So 1, 0 gets changed. So that's E1. It gets reflected across the vertical axis. And T of E1 is just going to be negative 1, 0. But E2 is sitting on the vertical axis. And so it's already sitting on the line across which we are reflecting, so it's not going to move at all. So E2 is the same as T of E2. So 0, 1 goes to 0, 1. And then we write down the matrix. The matrix has columns negative 1, 0, and 0, 1. Once again, we have an elementary matrix. This is just the 2 by 2 identity matrix with the first row multiplied by negative 1. Okay, so those are the three basic reflections in R2, and you can get other reflections from these. Let's look at an example. So the first example on your worksheet is this one. It says T is a reflection in the line y equals negative x. This is a linear transformation in R2. So this is not one of the three reflections that we just introduced. It's a completely different one. But what we're going to do in this problem is we're going to find the image of the vector 2, 3. But to do that, we're going to get the matrix. So here's a picture. There's the line y equals negative x. And we're going to take a vector, we're going to get the standard matrix for it by looking at the standard basis vectors. So here's E1. It's sitting on the x-axis. When we reflect that across the line, we're changing both of the components. So the components were 1, 0, and now we're T of E1 is going to be 0, negative 1. And then T of E2 was 0, 1, but that goes down, it was on the y-axis, but its image is going to be on the x-axis, and it's going to be negative 1, 0. So now let's write down those two images. T of E1 is 0, negative 1. T of E2 is negative 1, 0. And we can write down the matrix. It's the two columns are just the images of those two basis vectors. Notice that is not an elementary matrix. How many different elementary row operations do you have to do to the identity matrix to get this thing? You would have to swap the two rows. You would have to, that's one operation. Then another operation is multiplying one row by the scalar negative 1. And then the third operation would be multiplying the other row by the scalar negative 1. So there's actually 3 elementary row operations involved there. So there's 3 different elementary matrices that you'd have to multiply together to get A from elementary matrices. So this is not a single elementary matrix. So we're asked to find the image of the vector 2, 3. So to get that, we're just going to multiply by A. So when we multiply 2 times 0, that's 0, plus 3 times negative 1, we get negative 3. And then the second component is negative 2. So we can see that we've swapped the two components, we've multiplied the first component by negative 1, and we've multiplied the second component by negative 1. So there's 3 different things that we did to the vector 2, 3. So now we saw a couple of different vectors in some of the previous reflections that we did. We saw some vectors that didn't get moved at all. And so those are important. Those are called fixed points of the linear transformation. So here's the definition. So a vector V is called a fixed point of the linear transformation T when T of V is equal to V. So it doesn't get moved. So some linear transformations move some vectors, but not all of them. And so the ones that don't get moved at all are called fixed points of that particular linear transformation. So let's look at the linear transformation in that example we just did and find its fixed points. So we're going to find the fixed points of the linear transformation in that example. So here's the way we do it. We say, suppose V1, V2 is a fixed point. So T of V1, V2 has to be V1, V2. So that means that the matrix, the standard matrix A times V1, V2 has to be equal to V1, V2. And so if we do that product, we get 2 equations. We get negative V2 equals V1, and we get negative V1 equals V2. So these are 2 equivalent equations that basically say the 2 components are just opposites of each other. So those are actually just all the vectors that lie on the line y equals negative x. And we can visually see that if a vector is sitting on that line, let me draw a vector on that line. Let's make it purple. So let's draw a vector on that line. Call that V. It has components V1, V2. Oops. Then its image, when it gets reflected across that line, it can't move. So the image of a reflection across a line, the image of a vector that lies on that line is just that vector itself. So those are all fixed points. So let's write down the set of all fixed points. So we can write it as the set of all ordered pairs negative t, t, such that t is a real number. So that's a lot of fixed points. All right, so that's an introduction to reflections. Using the three basic reflections, the reflections across the horizontal axis, the reflections across the y-axis, the reflections across the line y equals x, and other types of reflections that are basically combinations of those three basic ones. So in other videos, we'll look at horizontal and vertical expansions and contractions, and we'll look at shears, and we'll do more examples.